So far, we've been talking about force on solid objects, like we spoke about the idea of gravity influence the force on an apple or the earth or moon and all that. Right? It was all solid objects. So now we'll shift our focus towards how this whole thing works on fluids like water and milk and oil and the other fluids. Let's start with a short experiment, and I've already drawn something here which we'll start thinking about it. Now, consider you have a jar of of the same volume, and let's consider the first jar which it has vacuum, right? It has no air particles or anything of that sort. So it just has vacuum, and you have a stone on the top, and you drop that stone. Now, obviously, that stone will yield to first of all, also this jar is placed on the earth, so it is under the influence of Earth's gravity. So obviously, the stone is going to hit the bottom soon, right? Now, what about the same jar when it has air particles in them, and you try to drop that stone from the same height? Of course, it's going to take slightly more time, right? Not because the Earth's gravity has changed, because there is going to be some resistance that the air particles are going to give you, and it's going to slightly take more time when compared to the same stone when it is dropped in a jar which has vacuum, right? Which has nothing, right? What about you do the same experiment on the same jar when it is filled with water? You can imagine, you can try this at home. Obviously, you'll see that stone is going to take a bit more time to reach the bottom because of the resistance provided by water. Now, if you really do an experiment with the same jar now with having another fluid, something like the milk, you will see that the jar is going to take, the stone is going to take even more time to reach the bottom. Now, the time that the same stone has taken has grown, has increased from here till here, and it's all because of the resistance provided by the medium here, right? Which is air in this case, which is water in this case, which is milk in this case. But in all the four situations, the stone has actually reached the bottom, which means that the mass of the stone was able to exert a certain amount of, to its weight, it was able to exert certain force, which made it, to the bottom. So we'll start focusing on these aspects here, and the way to visualize this, the movement of objects, or the movement of the stone on this, on any fluid is something like this, right? As the stone was dropped, right, in any fluid, let's consider this. Let's start with water, but think about it as this is going to be applicable for any fluid that we will consider, right? Let's discuss water first. So as you drop the stone, and when the stone was reaching towards the bottom, there are two forces, right, that is acting on the stone. The first one is the stone was able to exert through its weight. It was able to exert a force, and let's call it Fs. And that Fs is the force exerted by the stone by virtue of its mass, right? We understood the concept of weight, and the weight of the stone itself will make it fall, right? And when it is under the influence of gravity, right? And that is Fs. Now, the medium, which is water in this case, is also exerting a force, right, in the form of resistance. That's why that's why the stone takes more time in water, right? So the water is also exerting some upward force, right, to stop this stone, and let's call it Fw, right? And as long as this thing, right, Fs minus Fw is actually the net force that is acting, right, that is acting on the stone. And as long as this is non-zero, this net unbalanced force is non-zero, the stone will continue to sink. The stone will sink and it will hit the bottom, right? The force provided by the water or the medium is only going to delay the progress of the stone to reach the bottom, right? Now this force Fw is what we call as the buoyant force. The buoyant force. The upward force exerted by any liquid is what is called as buoyant force, and this concept is called buoyancy. And if an object is undergoing this force, it's called, this buoyancy. Now, what is the source of this force, right? I mean, we know the source of this force, right? The source of this force is obviously the weight of the body. Source of Fs is, the weight of that particular stone. That is a cause for this force. But what is the cause for this force, right? What is the cause for this buoyant force? Now, this cannot be the mass of this entire water, of course, right? This buoyant force is because the mass of this entire water is maybe it is likely going to be higher than this thing, and obviously it is the stone is still sinking, right? Which means that it is not you really cannot. It's not the mass of this entire the entire thing. But the answer is actually in the mass of the water per unit volume, right? And that's what we call as density. So the density is what is the cause for this buoyant force, and then density is nothing but your mass per unit volume. The density of the water. Is less when compared to the density of the stone, right? And that is what is causing the stone to sink, because it is not. This force is not large enough to overcome the weight of the stone, because the density of this mass, the density of the water is low. And the density of the water is actually higher than the density of air, and that is why the stone took quicker time. The resistance was less, and that's why the stone was able to fall sooner in the air. The same reason, the density, which is nothing but the mass per unit volume, the density of milk is more than the density of water, and that is the reason the stone took even more time to reach the bottom, right? So the buoyant force increases as we move from water to milk, because the density of milk as well as has increased, right? And that is why that is why the stone takes more time, and the buoyant force is relatively higher as compared to water, but still it is not high enough for it to overcome the weight of the stone, and that's why the stone still sinks, right? So the question now is, what is it that will make an object float, right? If you have to make an object float on water, what is it that you need to do? There are only two possible reasons. One is the object, the density, the nature of that object itself is such that it is less dense. Then it will definitely then it will float on top of the water. Relative to the water, if the density of that particular object is less, right, that object will float on that water. Or the other option is you can manipulate the structure of this object or the shape of this object such that you make it less dense. How do you make it less dense? By increasing the volume. We know that the volume plays a major role, right, in density, right? If you increase the volume of that particular object, then it will become less dense, and then the object will start floating in the water. So an example here is, think about a stone. Instead of a stone, let's say that you have a cube, right? You have a cube which is it's a solid cube. So let's consider the example of let's consider the example of a solid cube that you drop in water. Now that'll also fall and it will reach the bottom. But instead of a solid cube, if you have a hollow cube, right? When I say a hollow cube, it is filled with air, right? Now the difference between a solid cube and a hollow cube is that. Let's take this example. So in this case, you have You have the solid cube, and you have the and this is a solid cube, and this is a hollow cube, right? And in both the cases, the volume is the same. And in this case, let's say, because it has all solid particles, right? For this entire volume, it has all solid particles. But in this case, in this entire volume, it is only on the edge that it has solid particles. It is filled with air. So the overall density, right? What if you call the average density? Right? The average density of this hollow cube will be far less than the average density of this solid cube, right? Because it is filled with solids, right? This object is only dense on the edges, but not in the center, right? This object is dense all throughout, right? So this overall density is higher, so this will still sink. But if you can manipulate and reconstruct this cube such that you fill it with enough air so that this overall density becomes less than that of water, this object will float. It will not sink, because in that case your buoyant force will be more than the force exerted by the weight of this object, and which means that your density, and that's because the density of this object becomes less than the density of this, and this will start to float. And this is the concept. This is a basic concept on how ships are constructed, right? Why does a ship, when you have a how does a ship float in water? If you really think about it, on a let's take on water. If you have a ship, if you consider this, though the ship might be made of steel and iron, if you make a ball, a solid object out of this quantity of of this weight of the ship, it will sink in the water. But when it is designed like a ship like this, what you've basically done is you have manipulated or reconstructed the object such that its average density has reduced, because the ship's edges are having is made of steel, but it has enough it has air, right? All the cabin and all that is filled with air, so your total volume has increased, and which means that by increasing the volume you have actually decreased the density, because it is only dense on the edges, right? So that is the basic concept of why of how we construct ships. So far it's clear. So density plays a major role in determining whether your object either sinks or floats, right? So in this case, your density has been a source for this buoyant force, and that has made it come slower. In this case, your density has played a major role in making it even slower as compared to that of water. But how do we exactly we understood that density influences whether an object sinks or floats. But how do we exactly measure this thing? How do we exactly quantify this value, right? Because this we can quantify very clearly. Fs is something we can quantify, because if you know the mass of this particular stone and you multiply it by the gravity, we know that is Fs, right? Fs is equal to in this case, your Fs is going to be equal to mass of the stone times gravity, right? So that's very clear. But what about Fw? How do we quantify Fw, right? We obviously cannot take the entire mass of the water that is present in this, right? Because I mentioned earlier, it would be higher. It would definitely be higher, and that is not the right calculation. But how do we calculate Fw? And this is where the whole discovery of Archimedes comes into play, which we call Archimedes principle. And Archimedes was a Greek philosopher and physicist and scientist. And there is an interesting story on how we stumbled upon this particular concept and how we discovered this. But before we get there, let's see what that principle is all about. Before we formally state that principle, consider two objects. Let's take this jar. Let me use a different color. Let's consider two jars here. Let's consider this jar is filled with water till the brim, right? Till the brim it is filled with water, right? So this is all water. Now I have a I have a cube object. I have an object that is, you know, a solid cube, and I'm going to, try to drop this into this. Now, what will happen after some time? Obviously, this is a solid object. If I'm taking that the density of this object is more than the density of water, it will, sink, and at some point in time, it will come in here, right? The cube will land here, right, somewhere here. Now, what would have also happened is because the water was, it had water till the brim. It means that some water would have displaced from the jar, right? So you must have had some water drop out, right, from the jar because you have dropped this object inside this, and some part of this particular jar is now occupied by this cube. So the volume of this cube, right? What is the water that would have been displaced? It is the volume of the cube, volume occupied by this particular cube, right? Right. This is the amount of water that you would see outside, right? And here is where Archimedes, proposed that the force, right, the buoyant force, which is Fw, is equal to the force exerted by the mass of the displaced water. It's as simple as that. So if and how much is the mass of the displaced water? It is, what is the quantity of the displaced water? It is based on the volume of the object itself, right? So if this entire volume is now inside water, that the same volume of water is what you should have got it outside, and the weight of that is what is the buoyant force. It is as simple as that. So to come in here, so what this means is, so if I take this, so the buoyant force experienced, the buoyant force is buoyant force, or Fw, is equal to mass of the displaced water times gravity, right? Mass of the displaced water times gravity. And how do you know the mass of the displaced water? You can equate this to be equal to the density of the water times the volume times G, right? So this is so we are talking about the fluid, the water being the fluid, but this applies for any fluid, right? So your buoyant force is nothing but the mass of the displaced fluid or water times the gravity, and of course it has to be negative because it is an upward force, right? So there will be a negative sign to this because this comes from this is going against gravity. It's not going towards. It's not in line with gravity, so it has to be negative. So it is negative, and we know that mass is nothing but you can rewrite mass as your density times volume, because density is nothing but mass by volume and the overall volume, right? So this volume is the volume of the object here, and this is the density of the water. The density of the water times the volume of the object, right? The density of the thing gives you the mass. Pretty much gives you the mass of the water that is displaced, and when you multiply that with gravity, that gives you the buoyant force, right? So this is with respect to objects that are completely sinking, right? So in this case, the object is fully sunk, so the entire volume is what you consider here, right? So this volume is nothing but the volume of the keyboard here. What about objects that have not sunk, but that are the ones that are floating, right? So let's take that example here. So in this example, let's consider here also the water was up until the brim, and let's take now you have a ship, a small ship or a boat that is actually floating, right? Let's say that it is floating here. So even here, we say it's floating because it is not completely into it, but still there is some part of that ship that is inside the water, right? So that is this part. I'm going to use a different color. This part is the volume that is inside water, right? that is inside water. So in this case also, the Archimedes principle works in stating that the amount of quantity. What is the buoyant force here? So this is the buoyant force, which is Fw, and in this case also, Fw equals the mass of the displaced water times G, and which is nothing but going to be the density of the water times the volume. But in this case, the volume is not going to be the entire volume of the ship, but it is just the volume of the submerged part of the ship. It is only this volume that needs to be considered to capture the buoyant force of a floating object. So that's the key difference here. So the volume that is actually immersed is what would need to be used to determine the buoyant force for objects that are floating. But for objects that are fully submerged, you will take the volume of the entire object times the density, and you would be able to calculate the buoyant force. So so the formal definition for Archimedes' principle is when the object, right, when a body is immersed either fully or partially in a fluid, it experiences an upward force, which is called the buoyant force, that is equal to the weight of the fluid displaced by it. So that's your Archimedes principle, and let's write that out. So when an object is immersed fully or partially, it's fully because if it is able to sink, it is immersed fully. When it is partial, when it in the case of a boat which is which is just floating, right, partially in a fluid, it experiences an upward force, which is what is called buoyant force. Sorry, there's a spelling. That is equal to the weight of the fluid displaced by the object. So this is Archimedes' principle. When an object is immersed either fully or partially in a fluid, it experiences an upward force, the buoyant force, which is Fw, that is equal to the weight of the fluid displaced by that object. And the way you calculate that is, through the, if you have the density of that particular fluid, you need to multiply it by the volume of the displaced water, and that is nothing but the volume of the submerged part of the object. And you multiply it by G, you'll be able to get the buoyant force. So what is the story behind Archimedes? How did Archimedes stumble upon this discovery? So it is said that the king in Greece, he wanted to he employed a goldsmith to design and to make a golden crown for the queen and or for himself. But apparently the goldsmith came back with a golden crown, which he claimed to be a crown made of gold and made of certain mass. And when he told that to the king was not convinced. The king felt that the goldsmith has mixed something that is not gold and he has actually cheated him. And it was Archimedes who figured that out because what they didn't know was the aspect of density was not probably understood well by the goldsmith. So he thought that objects with the same mass would take the same volume, right? A 1 kg, say a more dense, something that is more dense a 1 kg of an object that is more dense will occupy less volume as compared to 1 kg of another object that is less dense. So think about it as, a 1 kg of iron will have less volume when you compare it with 1 kg of cotton, right? 1 kg of cotton will occupy more volume, right? Probably the goldsmith was not aware of that aspect. And the way Archimedes stumbled upon this was, he was thinking about this problem, and he went in. I mean, when he tried to take bath, his bathtub was filled with water, and when he got in, when he stepped into his tub, he saw the water to get displaced, just like how the water would displace when we place when we drop an object here. And that's what sparked the moment, and that is how we stumbled upon this idea that if indeed that was made of gold, right? If indeed that crown was made of gold, right? An actual he made another he took an equal volume of gold. And then he tried to immerse that in water to show that the amount of displaced water is actually different from that of the crown, and that is how, because that would reflect in their relative their densities, right? And that is how he was able to they were able to prove that the goldsmith had cheated, and that paved the way for the Archimedes principle. So before we move on, one last thing about densities. So far we have spoken about the densities of objects, and primarily densities of fluids. So in this case, it is the density of the fluid here is. We spoke about the density of water, density of milk, and any fluid. You can measure the density of any fluid, and there is a concept called relative density, and that relative density is nothing but relative density of an object is nothing but the density of an object divided by the density of water. So this is a useful concept because water is very common, right? It's the most common fluid, and many experiments in many problem statements, we will always, measure the densities of two fluids, maybe milk and oil or oil and mercury. Everything, we'll most likely measure that relative to water, because we know we experience water all the time. So more than comparing milk and water and mercury and all that, we'll only talk about, it will be a lot more convenient to talk about the relative densities with respect to water. Compared to water, is it more thicker or less thicker, or compared to water, is it more denser or less denser? So that quantity becomes very helpful at times. So this is that's what is called as a relative density of an object, and which is nothing but the ratio of that the density of that object over divided by the density of the water itself. So this is another concept. It might come in handy when we solve certain problems from a practical standpoint. Thank you.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.